Hey everyone! So, for today's lesson, we'll be talking about trees. And no, we're not delving into biology or forestry. We're talking about data structures that are visually and systematically represented and made similar to trees. In this lesson, we're learning all about what are trees, how they are represented, their parts, different types of trees such as their classification and subtypes, and how we traverse each type of tree. So what is a tree? Previously, we've tackled what linked lists are. To refresh your memory, they're nodes that point to other nodes, creating a linear collection of data. While a tree is a collection of nodes connected by direct edges. A tree is a nonlinear data structure compared to arrays, linked lists, stacks, and queues, which are linear data structures. Here's a visual representation of what a tree is. Now we need to know important terminologies to better understand what a tree is. Just like a real tree, it has its roots. In our case, that is our parent node, or the first node of the tree. We then have a child node where the parent node points to. Next is the connection between the parent and child node, which is called an edge. Children of the same parent node are called siblings. If a node doesn't have a child, then it is called a leaf node, seeing as it is at the end of the tree. A path is basically the entire connection of one subtree. So, in this path, we can see who are the descendants and ancestors of a node. The tree has varying levels as well, depending on how many parent and child nodes there are. The level starts at 0, so the root node is at level 0 and its children are at level 1. The children of the nodes at level 1 is then at level 2, and so on and so forth. The depth of a node refers to the length of the path from the root node to the selected node, while the height of a node refers to the length of the path from the deepest node to the selected node. Depth and height can also refer to the tree's length as well, which pertains to the length of the root to the deepest node of the tree. We also have the size of the node, which refers to the number of descendants the selected node has, including the node itself. There's what we call skew trees, where each node of the tree only has one child, except for the leaf node. Right skew trees, where the nodes only have one child at the right pointer, and left skew trees, where every node of the tree has only one child at the left pointer. Now that we know what a tree is and its parts, now we're going to talk about the different types of trees. We have a binary tree, binary search tree, AVL tree, and B tree. But for this lesson, we're going to only be talking about binary trees. First up, we have a binary tree. This type of tree restricts the parent node to only have at most 2 children. Now, this type of tree also has different subtypes. We have a strict binary tree, where each node should only have 2 or no children at all. Next, we have a full binary tree, where each node has exactly 2 children and all leaf nodes are of the same level. Next is a complete binary tree. This doesn't mean that this tree must be a full binary tree, as complete binary trees must have all levels, with the last level as an exception, be filled, and that most of the nodes should lean in to the left. Now, let's move on to the properties of binary trees. First up, we have number of nodes, which are calculated differently for full binary trees and complete binary trees. For binary trees, it is calculated as 2 raised to the power of h plus 1 minus 1. Where h is the number of levels of the tree. For complete binary trees, the number of nodes is in between the minimum and the maximum. So we calculate minimum as 2 raised to the power of h and 2 raised to the power of h plus 1 minus 1 for the maximum. For the next property of binary trees, we have the number of leaf nodes. And for a full binary tree, we calculate it as 2 raised to the power of h. The next property that we have of binary trees is the number of null-linked nodes. For complete binary trees, we calculate this with the equation n plus 1, where n is the total number of nodes of the tree. Now, you may be wondering, where are trees used? Well, they are used in compilers, data compression algorithms, binary search trees, and priority queues. Trees seem complex due to their links, and unlike lists, we don't traverse them in a linear selection. So there are 4 ways on how we can traverse a tree, which means the process where each node of the tree is visited. First is we have pre-order, next is in-order, post-order, and level order. First is pre-order. In this type of traversal, first we visit the root node, followed by the left nodes, and finally the right nodes. So in this example of traversing in pre-order, first is we visit the root node, so the order goes as 1, and then we visit the left nodes, wherein it is 2, and then 4, and finally the right nodes, where we go to 5, and then 3. So the order for pre-order is 1, 2, 4, 5, and 3. Next is we have in order. First is we visit all the nodes in the leftmost tree, then we visit the root node, and finally the nodes in the rightmost trees. So in this example of in-order traversing, first is we visit all the nodes in the leftmost tree, which starts from the bottom. So we start at 4, and then we visit the root node, so we move on to 2, and then the nodes in the rightmost trees, which is 5. Since we're all done here, we go to the next leftmost node, which is 1, and since there are no root nodes, since it is the root node, we move on to the rightmost tree, which is number 3. So the order for this example is 4, 2, 5, 1, and then 3. Next is we have post order. First is we visit all the nodes in the leftmost tree, then we visit the nodes in the rightmost tree, and finally the root nodes. So in this example of post order, first is we visit all the nodes in the leftmost tree, where again we start on the bottom. So first we start at 4, and then we visit the nodes in the rightmost tree, which is 5, and then finally the root nodes, which is 2. And then again we visit the nodes in the leftmost tree. Since there are no more nodes in the left, we go on to the right, which is 3, and finally the root nodes, which is 1. So the order for this type of traversing in this example is 4, 5, 2, 3, and then 1. And finally, we have level order. In this type of traversal, we visit the nodes starting from the first level, which is 0, where the root node is located. We then move on to the next level, which is the children of the root node, and so on and so forth. So in the next type of traversing, we have level order. In this example, first we visit the nodes starting from the level 0, where the root node is located. So first we start at 1, and then we go to the next level, wherein we start at 2, and then 3, and finally the last level, which is 4 and 5. So the order for this type of traversing is 1, 2, 3, 4, and then 5. And so you've reached the end of the video, and that's all for the basics of trees.